I'm Denley.
I'm Leif.
And this is our video report for OPTI 388 Lab 7 on Michelson interferometer applications.
Let's quickly go over our experimental setup. We're using, as the title would suggest, a Michelson interferometer to find the wavelength of 3 different sources, and we're doing that by observing their 8-inch fringe patterns. So there are 3 parts to this experiment. The first part involves actually calibrating the interferometer using a Hilding laser. Basically what we're doing is finding out for each turn of our micrometer, how far are we moving our mirror. That gives us information about our OPTI, and then from there, using our fringe patterns, we can actually get the wavelength of our light sources. Lastly, we're finding spots of destructive interference, and we're using that information to actually figure out the difference in wavelength of our sodium doublet source.
So for part A, we found the calibration factor for the interferometer. We counted 100 fringes through 170 microns of micrometer movements. We know the mirror movement distance of 100 lambda, where lambda is the wavelength of our Hilding source at 632.8 nanometer. Using this equation here, micrometer movements over OPD, we were able to calculate our calibration factor at 5.37294. So for part B, we had 3 different sources: a sodium source at 588.9 nanometer, a laser diode at 650 nanometer, and a mercury source at 546 nanometer. Then we were able to find these wavelengths experimentally using this equation here, which just is a function of our micrometer movement, how many fringes during that micrometer movement, and our calibration factor from the previous slide.
Okay, so for the sodium source, here's our results. We moved the micrometer 86 microns, and during that travel, we counted 50 fringes. Using that equation from that we got from the previous slide, we found an experimental wavelength of 640 nanometers. This is off by about 8.7%, kind of a big error, but there's a lot of potential sources of error in this experiment, including our initial calibration. It might not have been perfect, inaccuracies in counting the number of fringes, and also backlash in the micrometer.
For the laser diode, we did the exact same thing. We moved the micrometer 94 microns. This time we counted 54 fringes. This gives us a wavelength of 648 nanometers, 0.31% off our theoretical wavelength, and our sources of error are exactly the same as the previous part. Lastly,
we come to our mercury source. We moved the micrometer 91 microns, we counted 60 fringes. We found an experimental wavelength of 564.5 nanometers at a percent error of 3.4%. Again, the sources of error are identical.
So in reality, sodium has 2 lines, not just the one. They form their own interference patterns that, when added together, form an envelope and a carrier. By finding 2 successive 0 points, we can find the period of the second half of this equation here, and then by knowing the mirror displacement between those 2 points, we can find the wavelength, the separation between the 2 wavelengths of light.
Lastly, we come to our results. We found these as our 0 points. You see them right up there. We took the average between those, and then dividing by our calibration factor actually gave us that D source term, which is really our delta OPD. And then using that equation, we were able to find separation to be about 0.6609 nanometers, 6.6 angstroms, which is pretty close to the true separation of about 6 angstroms. 10.64% error, but on a small scale.